And to kind of intro that, how many, when I say 1 dozen, how many things is that? 12. Good. So if my eggs here, that's a dozen eggs. That's 12 things. Well, when I say 1 mole, what I'm talking about is 6.022 times 10 to the 23 things, or 602,000,000,000,000,000,000,000,000,000,000,000,000,000,000. That's how many things I'm talking about. That's a lot of things. But that's good for us when we're talking about chemicals, because most of the time I'm going to be talking about atoms or an element or a compound. And unless I get this many of an atom, I'm not going to be able to really start seeing it. So that's why I have to have so many of them. So you need your periodic table. If you didn't grab it out, please do so, because we're going to do some conversions. And we're going to use the dimensional analysis factor label method. We're going to go through bit by bit. So, first question I'm going to ask you, what is the mass? Question 1, what is the mass of 1 mole of O2? So when I'm doing dimensional analysis, the first thing I always start out with is my given. What's my given in this statement? 1 mole of O2. And I'm going to write out that whole thing. 1, and scientists make M-O-L-E into M-O-L, even though it really doesn't help all that much, but that's how they've taken to writing it. So that's how I'm going to write it. 1 mole of O2. 1 mole O2. Then I'm going to set up a fraction. I always need fractions when I'm dealing with dimensional analysis. So I'm going to multiply by some fraction. Now, I told you how to figure out molecular mass early this week, end of last week sometime. How do I figure out the molar mass of O2? 16 times 2, absolutely. So I look at the periodic table. The periodic table tells me that 1 oxygen is 16, and I have 2 oxygens here, so it's going to be multiplied by 2, so I have 32. Well, I purposely did not tell you the units before, but now I need to tell you, because otherwise we're going to be very lost. It is 32 grams per mole. That's my unit. From the periodic table, when I figure out my molecular or molar mass, that is grams per mole. So really what it's saying is that I have a ratio, and that ratio is 32 grams equal to 1 mole. That's what that's telling me. When I do dimensional analysis, I look at ratios to put information into my fraction. I always put the part of the ratio that I want to get rid of on the bottom, because it's like saying 2 times 1/2. What's that equal? 1, absolutely. You could do that by saying, well, half of 2 is 1. You could do it by typing it into your calculator. Or you could say, I have the same thing on the top and the bottom of a fraction, so they cancel out. All I'm left with is 1. I'm going to be doing that same thing here. I'm going to look at my ratio. 32 grams is equal to 1 mole. And I'm going to say I'm starting out with moles of O2 on the top of a fraction. I want to get rid of that. So I'm going to put 1 mole of O2 on the bottom. So now, just like I did with my 2's, canceling out 1's on the top, 1's on the bottom, I can cancel out moles of O2, which is good because I don't want moles of O2. I'm looking for mass. What unit do we use for mass here? Grams, absolutely. So I'm looking for an answer that has grams in it. I have to always put the other portion of my ratio on the other portion of my fraction. So 32 grams of O2 must go on top. Well, this is a nice easy one. 1 times 32 is 32. 32 divided by 1 is 32. So the mass of 1 mole of O2 is 32 grams. That's my question 1. What questions do you have so far? Yep.
Well, I'm just like confused, like 1 mole of O2, like why would the amount of moles change when it says that it's 6.02?
That's the number of molecules or atoms of it. That is the second part here. It says that number of atoms is equal to 1 mole. Well, 1 mole is equal to the mass from the periodic table. So it's like saying from before, we said that 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 760 torr, so on and so forth. I could go through all of those. They're just equivalencies. So what I'm really saying here is that, oh, I need more space. 1 mole is equal to 6.022 times 10 to the 23rd things. Might be atoms, might be molecules, might be something else. But that's also equal to the mass in grams from the periodic table of whatever thing I'm looking at. Good question. Thank you for stopping me, Anna. What other? Oh, yep.
Okay, so then why do you have to do all of it if it's just a mass that's on the periodic table?
Because sometimes it's not going to be giving us 1. That's an excellent question. So the first example that I gave us here was just 1. But many times it's going to be like, well, this person is 5 foot 6 inches tall. How many feet is that? We use our ratio of 1 foot is 12 inches. That's the same sort of thing we're going to be doing here. And we're doing it because of what we get in the lab. So we can measure out a mass in the lab and figure out how many moles that is, which is what this next question is. So let's look at our new one. Let's clear some space. Okay. So, question number 2. Maybe if it will let me. There we go. So, question number 2. How many moles are in 64 grams of O2? What's my given? Yeah, 64 grams of O2. So I'm going to start with that. Always start with your given. 62 grams O2.
64?
Sorry.
It's okay.
Thank you. 64 grams of O2. My ratio from before said that 1 mole is equal to how many grams of O2? 32, yeah, we figured that out by multiplying 2 by the mass of 16. So that's the ratio I'm going to use on my fraction. What am I going to put on the bottom? 32 grams of O2, so that my grams of O2 cancel out. What's the other part of my ratio that has to go on the top of my fraction then? 1 mole. Good. 1 mole of O2. So this one, all I have to do is multiply 64 by 1, just 64, and then divide by 32. What's my number of moles? 2. So I have 2 moles of O2 in 64 grams. So I could measure out 64 grams of oxygen, and then I would know that that means 2 moles. It's easier if we're thinking about solids. So let's say I measure out 64 grams of table salt. Well, I could figure out how many moles that is based on the mass from the periodic table of 1 sodium and 1 chlorine. Okay, so you could use this for anything, and it helps us when we're in the lab. That's where we're going to use mass and moles the most. And we're going to be adding 2 more steps to this stuff when we get to stoichiometry. For now, we're going to leave it at this. Questions before we move on? So, we're going to have 3 equations to memorize from today's notes. And the first one deals with Avogadro. Avogadro is the guy that came up with 6.022 times 10 to the 23. But he also did stuff with gases. And that's where this comes in. So here's our first equation. The amount of a gas is equal to the volume divided by the molar volume. And when we're talking about amount of gas, we're dealing with moles. So the moles is equal to the volume that we actually have divided by the molar volume. The big question should be, what is the molar volume? Well, it is a constant. It is always 22.4 moles over decimeters cubed at STP. STP stands for standard, temperature, and pressure. So this denominator is always going to be 22.4 moles over decimeter cubed. So memorize this equation, memorize molar volume. I want to note decimeters cubed is the same as what other unit? From our notes a couple days ago. Liters, excellent. Good. Okay, so what are these conditions of STP? They are 1 atmosphere as our pressure and 273 kelvins as our temperature. Okay, let's use our clickers. And I want to see if you can come up with the answer for this one. If this will let me. Work. You might need to wait a second on using the clickers. Hang on, sorry. Okay, it looks like it's going to let you in now. So how many moles of oxygen molecules are in 10 decimeter cubed at STP, standard temperature and pressure? And we've only done one equation so far, so you only have one possible equation to choose from. I'm going to do 3 more today, which might make other problems a little more tricky. gonna put 20 seconds on the clock. Get your clicker answer in, please. Bless you. Five seconds. Okay, we've got answers all over the board there. The answer was A. Let's take a look at how we figure that out. So we say moles are equal to whatever volume I have, which is 10 decimeters cubed, divided by 22.4 moles over decimeter cubed. There's a decimeter cubed per mole. Did I just write that down wrong? Okay. Okay. 10 divided by 22.4 gives you A. Yeah.
I'm confused. How did you get that?
How did I get what?
How did you get that equation?
From the last slide. Yep.
Oh,
So
okay.
the volume that it gives me in my problem is always divided by 22.4. Mm-hmm. Other questions? Yeah. Okay. Okay. We'll move on. We'll let it ruminate a bit. So, Avogadro's Law Part 2. So we could say that, well, if we change certain things, what's going to happen as a result? So if the temperature and pressure of a gas are held constant, the volume and number of moles are directly proportional, which means if I'm increasing the number of moles that I have, but I'm keeping everything like temperature and pressure constant, my volume's going to increase. So if you were doing your web lab the other day, and the pumps that you added into the little thing was adding more moles. That's what you were doing when you were pumping stuff in. You were adding more moles into it. Well, if you did not have volume as constant, the little guy would start walking backwards. And that's what the directly proportional means. If one goes up, the other goes up. Or if one goes down, the other goes down. Gabby. Ah, sorry. N, moles. Seems bizarre, doesn't it? N represents moles when we're talking about it in chemistry, even though it seems like it would make more sense to have it be M. But M's used in so many things like meters, milli, all of those things. So they chose N. Not quite sure what went into that. Thank you for asking that, Gabby. I forgot to mention it. Okay. So the equation, our second one to memorize, is this V1 over N1 is equal to V2 over N2. So our second one to memorize. And that's just saying some initial setup. The V1 is our initial conditions. And these are my ending or final conditions. You will always have 3 of these items. Could be any 3 of these 4 items. And one will be an unknown. And that's what you're going to be solving for. Let's try one. So, let's not try one. We might have time for that example later. We are going to first, though, do the combined gas laws. So, we have one variable that's going to be held constant, which makes life easier because then we don't have to deal with it at all. And then we're going to solve for some unknown, when we make a change to other variables. And here is the third equation for the day. P1, so the first pressure times the first volume, and my initial conditions, divided by the first temperature, is going to be equal to some final pressure times some final volume divided by some final temperature. What unit does temperature always have to be in for these problems? Kelvins, good. Okay. So let's take a look here. You can click in at any time if you know the answer. I'm going to be going through it step by step for those of you that need a little extra help with it. And I always like to do a couple of things right off the bat to get organized. The more organized you can be with these problems, the easier it's going to be to get the correct answer. So, I have pressure on 2.50 liters of anesthetic gas is changed from 760 millimeters of mercury to 304 millimeters of mercury. And I'm going to keep temperature constant. And I want to know what my new volume is going to be. So I'm not going to use my first two equations that are dealing with just volumes or volume in moles. But this one I'm going to use my combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. But I'm holding something constant. What am I holding constant? Temperature. So if it's not changing, I don't need to worry about it. So really what I'm dealing with here is P1 V1 is equal to P2 V2. And let's see what I have here. So I have, it tells me first, a volume of 2.50 liters. So that's my V1. And it is changed from 760 millimeters of mercury, so that must be my pressure one, P1, is equal to 760 millimeters of mercury. And it says it's changed to, so that's my P2, 304 millimeters of mercury. And it wants to know what the new volume is, so V2 is equal to something, and I want my unit to be in centimeters cubed. Is liters the same thing as centimeters cubed? It's not. So that means I'm going to have to make a conversion. And I could either make a conversion right away, or I could make a conversion at the very end. What would you guys like to do? End? Okay. Sounds good. We can do it at the end. I need to get this V2, the thing that I'm looking for, all by itself in this equation. And I could either plug in my numbers and then rearrange, or I could rearrange right away. I like rearranging right away just because it's easier for me to make sure that I'm putting stuff in the correct spot. So, right now I have V2 multiplied by P2. How do I get rid of multiplication? Division, absolutely. So I have to divide both sides by P2. What did I say happens when we have the same thing on the top and the bottom? It cancels out. Good. So those P2s cancel out. So the grand equation that I'm going to work with is V2 is equal to P1 times V1. I'm going to want to do that calculation first, so my calculator does not get confused. And that whole thing will be divided by P2. Now I should be able to just plug in my numbers. So, P1 is 760 millimeters of mercury. It's going to get multiplied by my V1, which is 2.50. working board. Oh dear. Okay. 2.50 liters. Again, I'm going to want to calculate that part first. Divided by my P2, which is 304 millimeters of mercury. What units cancel out? Millimeters of mercury, good. Which is good because I need something in volume, and liters almost gets me to the volume type that I want. Okay, this whole thing gets me 6.25 liters. Or I could say that that is 6.25 decimeters cubed. Is that what I want my answer to be? No. So what I want you to do is figure out what it would be in centimeters cubed. And I'll give you almost a minute to figure that out and click in your answer. We're down to 20 seconds. Centimeter cubed and milliliter are going to be the same thing. Excellent. The majority of you got C. To get from decimeters cubed to centimeters cubed, I'm going to multiply by 1,000, or just move the decimal place over 3 times to get C. Questions on that before we move on? Okay. So, yes, we will do this one. So let's assume that we have a constant pressure. So we know right off the bat that we're going to use the equation P1 times V1 over T1 is equal to P2 V2 over T2. Because we have nothing going on with moles here and we're doing changes. So I know of my 3 equations, this is the one I'm going to use. So we assume constant pressure. So which thing do I get rid of in my equation there? Yeah, P1 and P2. They can just go away because they're staying the same for the whole thing. So really I have an equation of V1 divided by T1 is equal to V2 divided by T2. I'm going to start looking at what my different variables are. So the 100 milliliter balloon, that's my first volume. So V1 is equal to 100 milliliters. And we have a temperature one equal to 38.0 degrees Celsius. I have a V2 that I want to know. I don't know what it is right now. And I want to know that in decimeters cubed. And my T2 is going to increase to 54.0 degrees C. What conversions do I need to make, Samantha? Yeah. Yep, so both of these need to be moved to Kelvin. So what do I add to each of them? 273, good. What other conversion will I need to make either at the beginning or the end? liters to decimeters cubed, which is the same as what other unit? Liters. Good. Okay. I'm going to keep writing stuff up here without saying anything. I want to see how many of you can work on it on your own and hopefully get the right answer. Where did... I'm gonna give you 20 more seconds. If you're feeling lost, look at the board. Who knows what the little dot, dot, dot triangle means? Therefore, yeah, it's good shorthand to know. Okay, let's see how we did. The majority of you are saying D. And that is what I got as well. Good. What questions do you all have? Get that one move out of the way. Yeah.
So, I'm not
Okay, look back at our notes from a couple days ago and you'll see that a decimeter cubed is the same as a liter. And hopefully you remember at some point, I don't know if in APES you did it or not, the conversions for the milliliters to liters and centimeters and all of those. What was that, Natalie? It was in your notes. Yeah. One more equation today. And we're going to skip that example for right now, and we're going to move on to what our last equation is. So the ideal gas law is a combination of Boyle's and Charles' law, which we're not going to talk about individually. Both of those two things come from the combined gas law. And Avogadro's law, which was the first one that we looked at, which was the V1 over N1 is V2 over N2. That was the second one, excuse me, that we looked at. Okay, the equation for our ideal gas law is PV is equal to nRT. P stands for pressure, So pressure times V, which is volume, is equal to N, which we said is a weird way of saying moles, times R, which we're going to talk about in a second, what all it is. You can read ahead in your notes a little bit, times temperature. You're going to have 4 things given to you, and you're going to have to figure out one for each of the problems that you get that deal with the ideal gas law. So, R is a given. It's a constant. It's one that you need to memorize. So we've got 2 things from here. We need to memorize the equation, but we also need to memorize what is this R. R is the universal gas constant. It is 0.0821, and the units for it, that's the thing that is not written on your sheet. It is liters times atmospheres divided by kelvins times moles. So if this is my unit, it means that my volume must be in liters to be able to be canceled out. Bless you. My pressure must be in atmospheres for it to be canceled out. My temperature, which we already know because of all gas laws, needs to be in kelvins for things to cancel out. And moles are always moles. Sometimes, though, you'll be given mass, and you have to use what we did at the very beginning of notes today to figure out what the number of moles is. Yep.
Okay, so say you have like deciliters cubed
Yeah.
or your volume, and you just convert it.
Yeah, yep, and it'll be the same value, you just write liters rather than decimeters cubed, yep. If, however, you're given something like millimeters of mercury, then you'll have to do a conversion from millimeters of mercury to atmospheres. Okay. So, let's look at our first example here. It says, how many moles, how many moles are in 3.00 liter sample of methane? CH4 is methane. You don't have to worry about that right now, but just so you know, that's methane. At 300 kelvins and 1.50 atmospheres. So I'm not dealing with any changes here, like I was with the combined gas laws, which means I'm going to be using PV is equal to nRT. Then I'm going to identify what I have. I have a volume equal to 3.00 liters. I have a temperature equal to 300 Kelvin. I have a pressure equal to 1.50 atmospheres. And R is a constant. It's the universal gas constant, so I'm going to write it down here. 0.0821 liters times atmospheres over kelvins times moles. And I am looking for moles, which is good because that's the only thing not already written up here, is something that I have. N is equal to some unknown at this point, moles. I want to get moles, so what do I have to do to get moles all on its own? Divide by RT, good. So PV over RT is going to be equal to the number of moles. At this point, I can just plug and chug. So pressure is 1.50 atmospheres. That'll get multiplied by my volume of 3.00 liters. That will get divided by my universal gas constant, 0.0821 liters atmospheres over Kelvin moles, multiplied by my temperature at 300 Kelvin. I can look at the units that I have. Atmospheres, I've got one on the top, one on the bottom, so those cancel out. Kelvin, I've got one on the top, one on the bottom, they cancel out. Liters, one on the top, one on the bottom, they cancel out. I am left with moles, which is very good because that's what I'm looking for. I'm going to give you a minute to get your answers in. Seconds. The majority of you got it. It is D. Some of you may have typed it into your calculator and your calculator thought that you were doing something different, unless you did things with the parentheses. So if you think that you typed all of that I have in purple there in the way that it says, then most likely your calculator just thought something different. So try again. See if you can get that answer. D is equal to 0.183. That is going to be it for today's notes. We have 5 minutes left of class. I want you to pull out that review. That is not homework, but it'll be a good thing to make sure that you have. It was on a yellow piece of paper from the very first day of school. You can also turn off your clickers, and they're going to go back in numerical order with the dark gray part facing the back of the classroom.
Are you sure that's right? I'm making mine off yours right now.